Let us consider another important concept in mathematics, namely function. Actually, the concept of function in mathematics is having a very long evolutionary history. Even when you were taught the concept of function, first your idea is that it is something like f of x is equal to x square or f of x is equal to x plus 3, etc. That was your basic idea. That is, first we thought that the functions means it's a polynomial function. That was the basic idea we had. And after that, then sometimes we considered the quotient of two functions. That is, f of x is equal to some quotient of two polynomials, rational functions. Then there came the trigonometric functions, exponential function, logarithmic function, etc. etc. So our view of functions become broader. The same thing happened in history also. And what is a function? What is the minimum properties you need for a function? Whether it should be continuous or not, whether it should be differentiable or not, whether it should be continuously differentiable or not. Such questions was there in the history of mathematics, and a lot of confusion was there in the beginning. And only after the calculus was developed to and the mathematical analysis was developed, only then the concept of function was generalized to a very general one, like it is an assignment of you are having two sets A and B, and to every element of A, a unique element of B is assigned. That definition came very late in mathematics. After some time, it was replaced by the set theoretic definition. That is, a function is not defined as an assignment like this, is defined as a relation, and the relation is nothing but a subset of the Cartesian product, and Cartesian product is nothing but a set of ordered pairs. So that is the latest definition. The point is that this latest definition is having a very long evolutionary history. The history of the concept of function is also very, very closely related with the history of mathematics. Okay, what is a function? A function is a relation. So let a function f from a set A to a set B is a relation from A to B such that for every x element of A, there exists a unique y element of B such that xy is such a relation is called a function. This is the modern definition. So a function from a set A to a set B is just a relation. And what is a relation? a relation is a subset of A cross B. And what is A cross B? A cross B is the collection of all ordered pairs xy where x is from A and y is from. So this relation is having a special property. What is the special property? The special property is that for every element x of A, there is a unique element y in B, so that x is related to y under this relation. That is, the ordered pair xy is an element of F. Only such relations are called functions. Actually, this specifies two properties. That is, first we specify that for every x element of A, there exists a y element of B such that the ordered pair xy is an element of F. That is the first part. Existence. For every x in A, there is an element in B to which that is related. That is first part. Second part is that y is unique. That is, the same y is not related to two different points of B. We can write for every x element of A and for every y1, y2 element of B, x y1 in F and x y2 in F implies y1 is equal to y. So first thing is, the first condition says that for every x there is one y to which that is related. Second condition stipulates that this y is unique. That is, no element is related to two distinct elements of. If both these conditions are satisfied, the relation is called a function. Only then it is called a function. And there is the same as for every x there is a unique y such that the ordered pair xy is an element of F. But instead of writing the ordered pair xy is in a relation F, the normal practice is that it is written as xfy. But in the case of a function f, we usually write it as y is equal to f of x. So this xy is an element of f is also written as y is equal to f of x. And here we say that y is the image of x under the function f. We say that y is the image of x under the function f. Or we say that f maps x to y. Or f takes x to y. Or we say that f assumes the value y at x. Or we say that f sends x to y. Or f transforms x to y. There are several ways of telling the same thing. And some people call function map alpha. They said that f is a map. Instead of saying that f is a function, some people call it map. Some people call it a mapping. Some people call it a transformation. There is another word, operator, which is used sometimes. For example, suppose a function f is from a to a. A function from a set to itself is usually called an operator. An operator is a function from a set to itself. That is, both a and b are the same. In general, function can be from one set to another set. But if both the sets are equal, that is, if the function is from one set to itself, such functions are sometimes called operator. And we usually write this way. F is a function from a to b. This is an abbreviation for writing f is a function from f colon a arrow b. That means f is a function from a to b. Here is a very simple example of a function. Suppose a is a set. Then we can consider a function I from a to a as follows. I of x is equal to x for every x. A is a set and every element x of a is mapped to the same x. Then there is a function. This function is called the identity function. For identity map. In fact, this is also a bit trivial because identity function does not do anything. Doesn't do anything. It maps an element x to x itself. So it's not moving it. It's not transforming it. But still, that is also considered as a function. Another, suppose A is a subset of B. Then we can define a function, say I sub A from A to B as I sub A of an element x is x for every x element of A. A is a subset of B. And every element of A is taken to the same element. Every element of A is in B. So, this is a function. This function is called the inclusion function. Actually, identity function is a special example where A is equal to B. When A is equal to B, this inclusion function becomes the identity function. So, identity function is a special case of inclusion function. Or inclusion map. If you take the set of all integers, set of all positive integers, then we can define a function f from set of all positive integers to the set of all positive integers by f of x is equal to x plus 1 for every x. Every positive integer, for every positive integer x, you can take x plus 1. That is uniquely defined. Therefore, that defines a function. Sometimes this is also called the successor of a integer. Successor of a positive integer. So this is a function. There is something called a constant function. What is a constant function? Suppose f is a function from a to b, and suppose that small c is an element of b, such that f of x is equal to c for every x element of a. That is, every element of a is mapped to the same element c of b. Such function is called a constant function. For each element b of c of b, we can define a constant function, taking all elements of a to that element. So there is a constant function. From real line to real line, any polynomial defines a function. If you say the function from real line to real line, f of x is defined as some polynomial. So suppose p is a polynomial, p of x is a polynomial. A polynomial defines a function because given any value of x, the value of the polynomial can be uniquely calculated. So that defines a function. So all polynomials define a function from real line to real line. But what about this? F of x is equal to 1 by x. It is not a polynomial, but it is a rational function. There is one polynomial divided by another polynomial with the rational coefficients. But the problem is that this is not a function from real line to real line. Why? When x is equal to 0, 1 by x, there is 1 by 0 is not defined. So this is not a function. Because if it is to be a function for every element of x, that is for every element of r, there should be mapped to an element here. But here 0 is not having an image. So this is not a function. So if you want to make it a function, you define like this. That is, if x is not equal to 0, we define it as like, and when you can also define f of 0 to be equal to say some, then it is a function. F of x is equal to sin x, f of x is equal to cos x, f of x is equal to for sin x and cos x, etc. define functions from real line to real line. But with the tangent of x, there will be a problem. What is the problem? Suppose f of x is defined as tan x, that is sin x by cos x. The problem is that when cos x is equal to 0, sin x by cos x is not defined. So there will be a problem. And for a function from one set to another should have value at all the points, and that value, secondly, that value should be unique. Now suppose we have a function f from x to y. Suppose that a is a subset of x. Then we can define f of a as the set of all f of x where x is an element of a. F is a function from a set x to and the set y, and A is a subset of X. Then we define f of A as the set of all f of X, X element of A. If this f of X is called the image of X. So this is the set of all images of elements of A. And what will be this? This will be clearly a subset of Y. This set is usually called the image of A under F. So every subset of A will be having an image, and that image will be a subset of Y. Important set is the image of the whole set X. This is usually called the range of F. So what is the range of F? It is the set of all f of X where X is in element of X. Clearly there is a subset of Y. If f is a function from X to Y, usually we say that X is the domain of F and Y is the codomain of F. If f is a function from X to Y, that is usually written like that: f colon X arrow Y. That is standard notation. Then X is called the domain of the function and Y is called the codomain of the function. And this range of F, that is f of X, is a subset of the codomain. The range can be very small. For example, in the case of constant function, what is a constant function? Constant function is a function which takes all elements of X to one particular element. So in that case, the range of F will be a singleton set. So there will be a very small subset of Y. And in some cases it can happen that the range and the codomain are one and the same. For example, in the case of identity function, suppose consider the identity function from A to A. Here, what is the range of, that is I of A? I of A is equal to A. So the range of I is also the same as the codomain of A. Sometimes can happen. You take say f as a function from real line to real line defined by f of X is equal to 2x, say, for every X element of it. Even though we define a function as a collection of ordered pairs, in practice a function is specified in this way. That is, we say that this is a function from this set to this set, that is, this is the domain and this is the codomain, and we will explain how the image of a particular element is calculated using some formula. Here f of X is equal to 2x. That is, the image of an element is obtained by multiplying 2 with that number. This is so this defines a function because this 2x is, for every x, 2x is uniquely defined. So this is a function. Now this is a function from real line to real line. No, so here this is the domain and this is the codomain. And what is the range of f in that case? That is f of r. What is that? That is nothing but r. Why? If you take any real number, say y, you can take y by 2. y by 2 is again a real number, and the image of y by 2 will be equal to y. So every element of the real line appears as the image. So here the range and the codomain are one and the same. So in some cases the range and codomain are one and the same. In some cases they may be different. If range and codomain are one and the same, such functions are called onto functions. Sometimes such functions are also called surjections, or we say that sometimes we say that f is a surjection. Or f is surjective. And this happens, that is a f from A to B is onto if for every y element of B there exists x an element of A such that f of x is equal to, that is every element of B appears as the image of some element of A. Such functions are called onto functions or surjective functions or surjections. Or f is onto if and only if f of x is equal to, f of A is equal to B. All functions are not surjective. For example, you consider the function f from real line to real line defined by f of x is equal to e to the power of x, the exponential of x for every x. Here for every real number x there is a unique e to the power of x in R. But what is the range of this function? That is, what is f of R then? It is not R, but it is just R minus 0. That is, 0 will not occur as the exponential of any real number. All other numbers occur as the image of some real number. So here this function is not onto. Actually, f of r, what is f of r? E to the power of x will always be positive also. So I should write it's the f of r is the set of all real numbers which are positive. Negative numbers will not occur as e to the power of x. So the image is the set of all positive real numbers. 0 will not occur as the image of the exponential function, and negative numbers will also will not occur as the image of. If you take the image of 0 will be 1, e to the power of 0 is equal to 1. The image of all numbers, all positive numbers will be greater than 1, and for numbers which are negative, for the negative numbers the exponential will be between 0 and 1. 0 will not be image, minus negative numbers also will not be image. So the range of this function will be the set of all positive real numbers. So this is not onto. And if you take the function real line to real line defined by sin x, the range of, there is f of r will be the interval, the closed interval minus 1 1. That is the set of all real numbers which are greater than or equal to minus 1 and less than or equal to plus 1. All values of the sign will lie between minus 1 and plus 1. And every element of this interval is the image of some x under the function set. So if you take the sine function, if you take the sine function f as a function from the real line to closed interval minus 1 1 defined by f of x is equal to sin x for every x, this function is onto. There is another important property of a function called one-one function or one-to-one function, one-one, or such functions are also called injections or injective functions. A function is injective if distinct elements are having distinct images. A function f from a set A to B is 1 1 if distinct elements of A have distinct images. More formally, we write f is 1 1 if for every x y element of A, f of x is equal to f of y implies a function is 1 1 if for two elements x and y, f of x and f of y are equal implies x is equal to y. There is another way of saying that x and y are different implies their images are different. For every x y in A, x not equal to y implies f of x not equal to y. These two statements are contrapositives of each other. This is P implies Q, this is not Q implies not P. Contrapositive. So such functions are called one-one functions. There are one-one functions, then there are functions which are not one-one. For example, if you take f of x is f from set of all integers to integers defined by f of x is equal to x plus 1 for every x. This is a one-one function. Why? If f of x is equal to f of y, that means x plus 1 is equal to y plus 1. That implies x is equal to y. Such functions are one-one functions. One-one functions are sometimes called injections or sometimes called injective functions. Sometimes called one-to-one functions. But some functions are not like that. For example, if you take a function f from the set of all integers to the set of all integers, f of x is equal to x square. Here, minus 2 square is the same as 2 square. So f of minus 2 is the same as f of 2, but 2 is different from minus 2. So this function is not one-one. Sine function from real line to real line is not one-one, because for two different numbers the sine can be the one and the same. The sine of 0 degree and sine of 180 degree are one and the same. So that function is not one-one. Actually, when we take sine as a function to real line, it is better to use radian notation rather than. So I should have told 0 radian and pi radian are having the same sine element. So there are functions which are one-one and there are functions which are not one. If a function is both one-one and onto, such functions are called one-one onto functions or bijections. So f from a to b is a bijection if it is an injection and a surjection. Or it is bijective if it is both injective and surjective. Injective and surjective. A bijection is a function which is both injective and surjective. That is, it is having the property one-one as well as onto. We can find several examples of such functions. For example, a function f from real line to real line defined by f of x is equal to x plus 1 for every real. You observe that this is one-one. This is also onto. Why? If you take any real number, say y minus 1 is a real number. The image of y minus 1 is y. So this is onto also. It's one-one and onto. A function is one-one does not mean that it is onto. And a function is onto does not mean that it is one-one. You can give several examples. If f is from positive integers to positive integers defined by f of x is equal to x plus 1 for every this is a 1 function, but this is not onto. Why? 1 is not the image of any number, so this is not onto. So this is 1 to 1, 1, but not onto. I can define again a function from integers, positive integers to positive integers like this. f of 1 is equal to 1, f of 2 is equal to 1, and f of n is equal to n minus 1 if n is greater than 2. f of 1 is equal to 1, f of 2 is equal to 1, f of 3 is equal to 2, f of 4 is equal to 3, f of 5 is equal to 4, etc. This function is not 1, 1. This function is not 1, 1. Why? Because f of 1 and f of 2 are the same. Distinct. 1 and 2 are distinct, but their images are not distinct. So this is not 1, 1. Not 1, 1. But that is onto. Why onto? Every positive integer occurs as the image. For 1 is the image of 1, 2 is the image of 3, 3 is the image of 4, 4 is the image of 5, etc. So every integer is the image of some element. So this is onto, but this is not 1. You can also find examples of 1. So we have the example of a 1, function which is not onto, and onto function which is not 1, 1. But for finite sets, this will not happen. If you take any finite set, say suppose A is a finite set, let A be a finite set, and suppose f is a function from A to A, then f is 1, 1 if and only if for a finite set A, a function f from A to A is 1, 1 if and only if it's onto, and onto if and only if 1, 1. But for an infinite set, that is not the case. Here we are having a 1, 1 function which is not onto, and an onto function which is not 1, 1. For a finite set, this will not happen. This is a very important property of finite sets, distinguishing it with the infinite sets, and we'll we'll discuss these things in detail later.